this is the chemistry Regents exam from January 2024, and yeah, let's see. Which particles surround the nucleus of an atom? Okay, so, like the basic model of an atom, this is the nucleus, and it has electron shells. So electrons surround the nucleus of an atom. These two are what makes up the nucleus of an atom, so that doesn't make sense. And this one is from nuclear chem. It's a type of emission, so this also doesn't make sense. Which conclusion was proposed as a result of an experiment? Okay, so this is referring to the gold foil experiment. They ask about this on every single Regents exam, so it's good to know that the conclusion they arrived to was that atoms have a small, dense, and positively charged nucleus. This is one of the earlier definitions of an atom, and this is outdated. Well, all of these are kind of outdated because now we know there's the wave mechanical model, but it's okay. And then the third one, atoms contain negatively charged particles. That wasn't discovered through this experiment necessarily, so this doesn't make sense. And this is the newest wave-like properties. So this is the wave. But that wasn't the result of the gold foil experiment. So what happened during this experiment was that Rutherford, the chemist who conducted the experiment, he was blasting alpha particles at a piece of gold foil. And then he discovered that some of the particles actually bounced back, and that was because of positively charged nucleus. Well, most of them went right through because atoms, they're like a tiny nucleus and large electron orbitals, I guess. So most of the light would go through, most of the alpha particles can go through, but if they were right onto the nucleus, they would bounce back out. So that's that. Mass of proton, neutron is this one. Yeah. This measures volume, milliliters, so this doesn't make sense. And then 1 mole, as you should know, is 6.022 times 10 to the 23rd somethings. So that doesn't really make sense, right? And then, can you imagine if a proton weighed 1 gram? Right, that's pretty massive. So this also doesn't really make sense. This is 1 U, which is AMU, which is atomic mass unit. And yeah, this one is the only one that really makes any sense at all. So it'd be this one. Then, which statement describes the relationship between 2 electrons, atom, magnesium, in the ground state? Electron, the first shell, has the same amount of energy. That's not true. Has greater energy. That's 1 2. That's not true. Second shell. That's not true. So that leaves only this one. 3. Yeah, this makes sense because this is the nucleus, right? It's positively charged because it has protons, which is positive, plus neutrons, no charge. And then these are the electron shells, right? And they're negatively charged. So opposites attract and like repel. So the first shell, the electrons are closest to the positively charged nucleus, which means that they have the least amount of energy. So farther away from the nucleus means more energy. So this number 4 is the only one that is correct. Okay, so going from ground state to excited state, they absorb energy. So, for example, an atom needs to absorb energy, and then one of its electrons will go up to a higher energy level. This is what happens when it returns from the excited state. Atoms, they can't randomly increase or decrease in mass number. So that doesn't really make sense. Chemical property of copper. So color, this is a physical property, can be flattened, this is malleability. Reacting, that's basically the keyword you look for. Like when it's asking for a chemical property of something, if it says reacts, then you can pretty much be sure that that is the chemical property. And then the fact that it asks as a conductor is also physical. STP, two forms of solid, have different properties because different crystal structure, different structures. So yeah, they have different properties because they have different structure. That makes sense, right? Because I guess if you have just one branch versus if you have a bundle of branches, these have different structures, therefore they have different properties. This, easy to break. This, harder to break. Because of the fact that their physical structures are different, right? Okay. And then it says, which element has highest first ionization energy? Okay, so this one you can just look in the reference table. You can, pretty sure it's table S. Yep, it's table S. So period 2 would just be like the horizontally the one that starts with lithium. And then if you look, actually you can do it 2 ways. You can either look at like just the periodic table trends, or you can look at table S. The second option is more time consuming, but it's a lot easier, I guess, because yeah. And so I'm just gonna do it based on periodicity. From left to right, first ionization is increasing because, okay, left to right, i.e. up, because the size of the nucleus increases as you're gaining more protons moving to the right side along a period, right? Like it's period 2 starts with lithium, and that has 3 protons, and then ending at neon, it has 10 protons because it's element number 10 with 10 protons. So it has a bigger nucleus, which means increased force of attraction, which makes it harder to take electrons away, right? Because if you have a bigger nucleus and a stronger force of attraction, it's harder to take away electrons because the electrons are attracted to the big proton. To the big nucleus. So 3 here. Which phrase describes a specific compound? Describes a compound. Compound contains, by definition, more than one element, so this is not right. Physically separated into elements. How would you do that? Physically separated into elements? That's kind of is composed of elements chemically combined in a definite ratio. So this one is the one that makes the most sense, right? Let's see what the last one is first. It's composed of elements mixed in proportion. They cannot vary. Yeah. Like, for example, this is ammonia. It's 1N plus 3 H's. This cannot vary. No change ratio. Wow, what is this caveman language? And then this is NH4. This is ammonium, and it's 1N plus 4 H's. And this, it can't change either. Because if you change it, you're changing the compound. It's a different thing. So, yeah, it's a definite ratio. The first two are like obviously wrong. And then number 4 is pretty evident too, that ratio of the elements that make up the compound cannot vary. So number 10 asks which chemical formula shows the arrangement of atoms in a molecule. So let's just use pentane as an example. The empirical maybe let's use hexane instead. 2, 3, 4, 5, 6. The empirical formula of hexane. Wait, let's write the molecular formula first. I can't do this. So the empirical formula here would be, because it's the simplest whole number ratio, right? Whole number. And then that doesn't tell you anything about the structure. Then this is the molecular formula, which also doesn't tell you anything about the structure. And then the general formula would just be like, I think it's the one that's just like the ratios. So this is ratios. So for like a hexane, it would be, right, which also doesn't tell you anything about the structure. Well, number 4, I think it would be like this. You know, for a hexane, however many that has. So number 4 would be one that makes the most sense, because this would be like CH3, CH2, CH2, and it just keeps going, because hexane has 6 carbons. I don't want to draw all of them. Anyways, a 2.5 liter sample of SO2 STP can be differentiated by comparing their, so tells us that they're at STP, so cannot differentiate by temperatures. Both of them are gases at STP, so we're not differentiating by phases. We have 2.5 liters, cannot be differentiating by volumes. The only one that makes sense would be masses. If you wanted to determine the mass, you would do it stoichiometrically. 2.5 liters, 22.4 moles of gas, and then moles of gas to mass is, you just multiply by the gram formula mass. Yeah. Which terms two different categories of compounds? Okay. These are the same, covalent and molecular, pretty much used interchangeably in Regents Chem. Thermal is not a category of compounds, I don't think, so it's just ionic and molecular. Ionic being metal plus non-metal, and then covalent or molecular is non-metal plus non-metal. Which molecule contains a multiple covalent bond? So hydrogen can't make double bonds. It only goes like that because it's a duet, not an octet. And then both of these are halogens. So they're both bonding like this, and then Br is like this. So it would just be O2 because oxygen has 6 valence electrons, and then and then so the oxygen would be like, and this is a multiple covalent bond. So yeah. Symmetrical in shape and distribution of charge. So right off the bat, you can tell it's methane, but you can go through it like individually. So HCl, this would be the Lewis structure. Wow, this autocorrect is kind of annoying. This is the distribution of charges. Hydrogen is partial positive because compared to chlorine, it has a lower electronegativity. It's like 2.2 versus chlorine 3 point something. So the distribution of charge is asymmetrical because you have a partial positive on one side and a partial negative on one side, right? So that's that. And then H2O Lewis dot structure is like this. H's again are partially positive, and then O is partially negative. So if you draw a line of symmetry, you can tell that it's asymmetrical. Asymmetrical. And then NH3 is like this, and the H's are again partially positive, negative. So if you look at the symmetry, it's again asymmetrical. And then CH4, it's positive, partially positive, and then partially negative here. And if you draw lines of symmetry, you'll see that this one is actually symmetrical. Yay! Exclamation mark for enthusiasm. What occurs when 2 atoms of bromine react to form? Okay, so I can use the handy dandy mnemonic: break, absorb, forming bonds, release energy. So when 2 atoms of bromine react to form a molecule of bromine, it's these 2, right? Yes. So form as energy is released. Atoms of which element have the strongest attraction? Oh, so the highest. This one is fluorine. You can either, again, periodic trends or table S. So in terms of periodicity, the trends for fluorine, for electronegativity is like, this is your periodic table. Very rough drawing. And the trends increase this way. So as you get to the top right corner, you have the highest electronegativity. And then if you don't want to remember how to do that, you can just go on table S. Fluorine has 4.0, and it's the highest one out of all of them. So heat flows from an object at a room temperature to an object. Okay. Always where it's hot to where it's not. So this is the hot, not. So from that we just know that the object is less than 20 degrees Celsius. Which choice is less than 20 degrees Celsius? It's 1. So it's 15. According to the kinetic molecular theory, ideal gas has particles with definitely not large volume, no attractive forces. That is the ideal gas. Ideal gases travel always in random motion. Always random motion. Straight line, random straight line motion. So it's not D. Okay. It would just same volume at STP equals same number of moles. And the same number of moles means that it's the same number of molecules, given that they're both, molecules, given that they're both not diatomic. It's not like one is monoatomic and one is diatomic, right? So yeah, same number of moles equals same number of molecules. Then all chemical systems at equilibrium have, that's not true, not necessarily equal, but not changing concentrations. Rates, yup. Rates of forward and reverse reactions. Activation energies, that just doesn't make sense. Okay. Which expression represents the heat of reaction? Okay, so heat of reaction delta H, you find this. This is delta H. So it's the PE products minus PE reactants. Products minus reactants. Which phase change represents an increase in entropy? So increase in entropy means an increased disorder and increasing entropy. Because solids, they have a uniform shape, they have a definite volume, so very low randomness. And gases are all dispersed everywhere, so this is very random. Okay, you get the point. So it would just be this one to this one. Because liquid to solid, you're decreasing again. Gas to solid, decreasing by a lot. Gas to liquid, decreasing. And then liquid to gas, it's going from a liquid which has a moderate amount of randomness to a gas which has a lot of randomness. So that would be an increase in entropy. In nature, tend to go low energy, high entropy. Yep. Yeah, if you guys do end up taking AP Chem, there's a table about like the spontaneity of reactions, and it's pretty interesting. But anyways, there's one that's always like, wow, this one, if it has all these qualities, it's definitely spontaneous despite temperature. And it's at positive delta S, negative delta H. So this is the disorder. This is the energy. Because there's this formula to determine the Gibbs free energy, the spontaneity of reaction. So yeah, anyways, very random tangents. Sorry about that. But you just, for the disorder, you can think of it like, this is like an analogy every one of my chemistry teachers used. The disorder is like my bedroom. I'm a very disorganized person. So as the week goes on, my bedroom gets more and more chaotic and messy with papers all over everywhere. Yeah, I don't organize my desk at all. So, well, no, actually every month, I guess. Or every week. Depends on, but anyways, it's just over time, my desk gets more and more messy because I'm just like that. So, systems in nature tend towards greater disorder. So you can cross out numbers 1 and 3. Shh. My dog is sad. And then just think of these two reactions. Which one do you think is more spontaneous or more likely to happen? This one, right? Because look at the activation energy. It's so small. That means the reactant particles don't have to gain that much energy in order to overcome that barrier. So systems in nature tend towards lower energy and higher entropy. It's good to remember that. It's almost like muscle memory saying that phrase. Low energy, high entropy. Which name represents a hydrocarbon? This is a halocarbon. This is a ketone. This is an alcohol. This is a hydrocarbon. Just look at this parts or the suffixes. Which process occurs at the anode in an electrolytic cell? Starts at the anode. Electrons are lost at the anode. Or an ox, red, cat. Anode, oxidation. Reduction happens at the cathode. So these two are not in electrolytic cells. So, yeah. And then this one's the cathode, obviously. Which formula represents an electrolyte? Electrolyte. This is not an electrolyte. This is also not an electrolyte. This just goes AQ. It would just be this one. It would just be number 3. Because this is an acid. So it dissociates pretty readily. Since these are both ions, they conduct electricity. Because mobile ions conduct electricity, right? Mobile ions conduct electricity. So yeah. I don't know if this is given, but you can't really have aqueous water. That's pretty that's pretty silly. Arrhenius acid. You can look at the reference table, or which one is able to give off a H+. So these two are, actually just this one. Since this is a hydroxyl group, you can't give off the H here. That's a big no-no. So it's not number 4. And then ammonia is a pretty common weak base. So this is also a big no-no because it takes in hydrogens instead of gives out hydrogens. So it takes in one and becomes an H4. And then this one just doesn't really make sense. It doesn't even have any H's to give, but this one would be the answer because hydrochloric acid, it can give away the H plus, and it gives it away pretty readily, which makes it a strong acid. So one of the 7. According to acid-base theory, okay, we just talked about this. So acids, they don't deal with hydroxides. They're not associated with OHs, so you can cross out 1 and 3. And acid is one that donates. It gives H away, right? So there's a acronym my teacher came up with: bases accept H's and acids donate them H's. So yeah, it's that. And then which nuclear emission has the greatest mass and ionizing power? Oh, my leg is numb. Okay. Greatest mass. This one just gives it away. It's the alpha particle. Gamma radiation, this has very, 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 very little mass. But it has the greatest penetrating power. But that's not what the question's asking, so yeah. This one you can find in somewhere on the reference table O. Table O. It tells you that the alpha particle is essentially like a helium atom. It's got a mass number of 4, so that's pretty big. And then beta is 0, gamma is 0, and positron is 0. 0, 0, 0, 4. It's most massive out of all of them. Which describes a benefit. I feel like they ask this every year. Large amount of energy. Nuclear reactions, energy efficient. They produce much more energy per reactant. Versus typical chemical reactions. And if you didn't know that, it's okay. We can read the options and pretty much find that out too. So large amounts of water are needed. This is not really a benefit. This sounds like a downside. Power plants can be. That's just not true. There's carbon dating and using the half-lives of radioactive isotopes to determine relatively how old something is, but that's not using power plant reactions. And then radioactive isotopes are stored for a very long time at the power plant site. That also doesn't really sound like a benefit, so none of these are really benefits, and that's how you can tell. Which elements are present in the mixture? So you can look at the mixture. Definitely has E. and cross these two out. And then G and J. Since it has the double here, it's G. None of the noble gases are diatomic. So it can only be this one. First of all, these two are not even elements. Not elements. It's a combination of this and this, which are different elements. I hate this autocorrect. How do I turn this off? Different elements. So yeah, just number 2. This is also just a diatomic and not a noble gas, because none of the noble gases are diatomic. Noble gas. 33. A student determines the density of a copper sample at room temperature to be 9.46. Based on table S, what is the student's percent error? So the percent error formula is on the back. It's measured minus accepted over accepted times 100. And then according to table S, the density of copper is 8.96. So you do 9.46 minus 8.96, 8.96 times 100. I got 5.58. Closest to 5.6. Then gram formula mass of MgNO3 2. So since we have this, we know we have 2 NO3s, 2 nitrates. So look on the reference table, on the periodic table for the masses. Mg is 24.3. 2 times 14 plus 16 times 3. That gives you this one. So if you set it out, it's just magnesium, 24.3, plus 2 times, since we have 2 nitrates, 14 plus 16 plus 16 plus 16. So 2 times 14 plus 16 times 3. Yeah. Oh, plus that. Compared to rubidium, Rb plus ion has, okay, so it's a positive ion, which means that it lost an electron. So 1 and 2 are wrong. It's a positive ion because electrons, negative charge. So if you lose a negative, equals +1 overall, if that makes sense. Because 2 negatives make a positive, right? So, yeah. So it has 1 fewer electron, and since it lost an electron, it now has a smaller radius. Why? Well, that's because rubidium is in rubidium is a group 1. It's in group 1. So after losing the 1 electron, it would have the same electron configuration, same config as krypton. So it would be a much smaller radius. And so this 36 asks about same. Okay, so this is like asking about the same concept, neon in the ground state. So that would just be sodium. Wait. Ooh, let's try that again. Okay, so 36 asks about a similar concept, which would have the same configuration. Okay, so K minus 1, this is AR. This one is helium. This one is neon. This one is argon. So it'd be this. So for these two, add 1 electron to configuration. These two, minus 1 electron. So yeah. This one asks about which, okay. So this is an aldehyde compound. It's okay. Shh. My dog is still sad. She wants to go outside, but it's raining outside. Man, New York weather. Then methane, this is the alkane. This is a compound. Alcohol, also compound. This is an element. This is number 56. I'm still a little sick. The difference in which property allows for the separation by filter paper. Particle size. I think this one is just testing you on general knowledge too, to be honest, because yeah, you know how filtering works. Just because the sand is like this big compared to the waters that are like super small, not to scale. Okay, according to 39, which compound has very low solubility? Oh, I hate reading that table. Ugh. Oh. Okay. So these two are sodium. Sodium is always pretty good with solubility because it's a group 1 ion. So it's not those two. And calcium hydroxide, this is okay, you can go. This is a strong base. Not that you need to know that, but just for poops and giggles, it's a strong base, which means that it's able to dissociate like this. Oh. So yeah, it's not this either. It's just 4. And yeah, you can also just tell by looking at the table F. It says phosphates are generally insoluble except when combined with group 1 or ammonium. And calcium is not group 1, calcium is group 2. So it's not an exception to the insolubility of phosphate. What is the molarity of a okay, molarity equals moles over liter. So 0.125 mole over 0.200 liters. Type that into your calculator and shh, I'll let you go in a second, please. Just be quiet. It's this one. Compared to blah 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 blah. Okay, so this less concentrated because it's fewer moles per liter, right? And this is more concentrated. So when you have a more concentrated solution, the boiling points and the freezing points, they go more extreme. So you have a lower boiling point. You have a lower freezing point and you would have a higher boiling point. That's how That works, so that'd be number 2. This happens because the dissolved ions in the solution, they make it harder for water to freeze because there's all these little thingies, colligative properties. They make it harder for water to freeze. Like, think of this. This is what frozen water looks like, right? Just imagine these white things are water molecules. Frozen water. But now, ions, not water. But now, when you have a solution of something, you have these waters, they're trying to freeze, but there's interrupting things, you see? So yeah, this is also why this is also why there's salt on the roads in the winter here in New York. It's because they don't want the roads to freeze over as easily, so they put salt to lower the freezing point. And then in terms of boiling point, there's intermolecular forces between the ions and the liquid water, and IMFs. Strong intermolecular forces make it harder for water to boil because the particles of water, they require more energy to overcome that phase barrier with the additional intermolecular forces that exist between the ions and the water molecules. So, yeah, that's that. What is the temperature in degrees Celsius of a sample of matter at 35 K? So this formula is found somewhere on your reference table, but 35 plus 273 equals degrees Celsius. This one. Wait. No. Let's try that again. Okay. What is the temperature in degrees Celsius of a sample 35K? 35K, we know that's pretty cold. 0K is absolute 0. So it can't be these two. It's just 35 minus 273. It's Celsius. I think it's this one. Next question. I can't. My iPad's not scrolling right. Oh my god. Which graph represents the relationship pressure and volume ideal gas at constant temperature? This is just funky. Oh my gosh. And this doesn't make sense. Be this one. Yeah. This one also doesn't make sense. So, what this is saying is that when the pressure is low, high volume, but as you start to increase the pressure, the volume decreases. That makes sense because if you think of, like, this is a small container, small v. This is a big container, big V. Pressure, by definition, is the force and frequency of collisions against a container wall. So when you have a small volume, you obviously have a higher pressure because the particles inside the container, they're in a very small container, right? So inevitably, they collide more with the container walls. But when you have, like, a bigger container, there's more space for the particles to go, so there's less frequent collisions. Which represents a physical change. Okay, so this is a chemical reaction. This is a physical. This is just a sublimation, solid to gas in one step. So yeah. 45. Which fastest reaction rate. Okay, so you want highest concentration, high temperature, high surface area, or the addition of a catalyst, but I'm assuming they're not mentioning catalysts in this multiple choice. So strip of zinc versus powdered zinc. Powdered zinc has more surface area. And then which one's more concentrated? This one's more concentrated. 0.2 is less than 2.0 molar. Redox reaction. So there's a change in oxidation numbers. It's this one. Because going from left to right, the iron was oxidized, and this was reduced. Because we know that because the Fe, the oxidation number on the right, it went from 0 to Fe to +3. So there's an increase in oxidation number, which means that this was oxidized. And then the oxygen, it went from 0 to -2. That is a decrease in oxidation number, which means that it was reduced, which represents blah 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 blah. So reduction half reaction, from here to here, this is 0 to 1. That is not decrease in oxidation number. 0 to 1, again, not decreased in oxidation number. And then both of these are 1 to 0, but we have to look which one makes sense. 1 equals 0 plus -1. Whoa, that's crazy. We're breaking math. Plus -1 equals 0. Which one makes sense? Number 4 makes sense, right? Because the first one, how can 1 equals 0 minus 1? That's just silly. And then the pH value of a solution is changed from 6 to 4, which phrase describes the change hydronium concentration. Okay, so it can't be, it's not by factors of 2, it's by factors. So a change of 1.0 on the pH scale is 10-folds of concentration of hydronium. So 6 to 4, more acidic, increased. Which type of cell? There's a power source, electrolytic, electroplating, whatever. Electrolytic, yeah. It's not a voltaic cell because voltaic cells don't need an energy source because they're spontaneous. This one is an electrolytic cell that uses chemical energy to produce, uses electrical energy to produce a chemical change. They're using the electrical energy from the battery to electroplate. Electroplate. I promise my spelling is not usually this bad. Just hard to talk while writing simultaneously. Which equation represents a fusion reaction? Fusion. Very important. Means small plus small equals big. So this is not right. This is not right. And it's just this one. It's deuterium and tritium going to a helium. try this again. Let us try this again. Okay. Okay, so which reaction represents a nuclear fusion reaction? So fusion, what does that mean? It means to fuse, to combine small plus small. So this one we see a big thing and it's breaking apart. So that's not right. This is also a big thing and it's undergoing positron emission. This is a positron. That's also a no. This won't be a yes because it's deuterium and tritium combining to form helium and a neutron. And then, yeah, since we have the right answer, we don't have to look at the next one. Now for the FRQ section. Let's see. Molecular formula, empirical formula of a massive 180 grams per mole. Okay. This is just sugar, right? Okay. I just know this because I don't know. I see sugar all the time, so. But yeah, what you would do on the test is, this is the empirical formula, so it represents the simplest whole number ratio. So you can keep like multiplying it until you get 180 grams per mole. Say you can try to multiply this by 6. By 6. So you get C6H12O6, which is sugar. And then you calculate the molar mass by doing 12.01 times 6 plus about 12 times, approximately 1, plus 6 times basically 16, and you would get 180. State the trend in atomic radius for these 4 elements. Which 4? Oh! I never read I should probably start reading. So these are halogens in order of increasing atomic number. So it would go fluorine, chlorine, bromine, and iodine. So atomic radius is increasing. Radius is increasing because as you're going from F, Cl, Br, and I, you're going down. You're going down group 17. Going down group 17, which means that you're increasing the number of electron shells. Volume of 2.5, density equals mass over volume. The density of iodine can be found on table S, and that's 4.933. 4.933 equals mass divided by volume 2.5. So 4.33 times 2 times 2.5. 4.933 times 2.5. 12.3325. 12.3325. You can round this or not. I don't think they really care. So 12.333. State, in terms of electrons, why these elements have similar chemical properties. They have the same number of valence electrons. Since they're all in the same group, that means that automatically means that they have the same number of valence electrons. So when they have the same number of outermost electrons, their reactivity is pretty similar, which gives them similar chemical properties. State the molecular polarity. So we have partially negative, partial negative, partial positive. If you draw a line of symmetry, you see that this is symmetrical. So this is a nonpolar molecule. Based on table S, determine electronegativity difference between oxygen and calcium in calcium oxide. So the electronegativity, wow, this is so thoughtful. They even tell you where to go. Electronegativity of oxygen is 3.4. And calcium is 1.0. 3.4 minus 1.0 is 2.4. That'll be your answer, is 2.4. Classify in terms of saturation type of solution produced. 20 grams of ammonium chloride in 25 Celsius. No undissolved ammonium chloride remains. Let's see. Take a quick look at table G. So at 20 degrees Celsius, you're able to dissolve about 37-ish grams of ammonium chloride to produce a saturated solution. So since it's 20 is less than 37, this is an unsaturated solution. State evidence from table I indicates dissolving process endothermic. Okay, so this is the fifth one from the bottom, NH4Cl, NH4Cs. Since we have a positive delta H value, this means that the reaction is endothermic. And yeah, I think this is all you need, like positive delta H value of 14.78 kilojoules per mole. That's all the evidence you need to justify that. To explain, to use as evidence that this process is endothermic. Like, if we were to draw a potential energy diagram, this would look something like this. Right, because the delta H here is positive. Products minus reactants is positive. So that's endothermic. State in terms of particle distribution why the solution is classified as a homogeneous mixture. Particle distribution, why it's homogeneous. Particles are evenly distributed. That's what makes a mixture a homogeneous mixture. The fact that the particles are evenly dispersed throughout, that is what makes a mixture homogeneous. Like, if it were uneven, that would be heterogeneous. So, yeah. Average distance between the particles. So this is the gas phase, asking for where it's in the gaseous phase. That'd be E to F. So it starts as a solid, right? It's a solid, and then it's melting. It's a liquid, and it's being vaporized. And then it's a gas. So it's E to F here is where it's a gas. State what happens to the potential energy of the particles during the melting of the substance. So during the melting, like right here, the potential energy increases. Because when you're going from solids like this to a liquid like this, you have more potential energy. Why is this a hand? I drew an arrow. It's like that, right? So you have more potential energy as you're going from solid to liquid, and you gain more potential energy as you're going from liquid to a gas. So, yeah. Bromocrussel 1 molar. So this is a strong base. And that means it's basic. Was it table M? Table L? Table M. Oh. Bohr crystal green is blue in basic solutions. So this would be blue. Say number of sig figs used to express the concentration. Oopsies. Did I? Oh, wait. It's already given. This is the concentration. It's 2 sig figs. Yeah, leading zeros never count, and zeros don't count. And trailing zeros count if there's a decimal point. Determine the concentration of the HCl sample using titration data. So M1V1 equals M2V2. 30 mil equals 18 mil, 0.1 molar. So if we do 18 times 0.1 divided by 30, we get 0.06. So that's our molarity of our acid. Concentration, molarity, same difference. Compare the hydroxide ion with the hydroxide ion then resulting. So there's more hydroxide in the KOH solution, more in KOH solution. Oh, what just happened? Ooh, that's kind of not good. How do I change? No, this is so terrible. A replay. Oh, fixed it. More in KOH solution than the resulting neutral solution. Why? That's because the resulting solution is neutral, silly goose. The original one is a basic solution, since we already said that it would be blue and brown crystal green, right? So it's more on, well, actually, being blue and brown crystal green doesn't say much because as long as you're over 5.4, you're blue. But anyways, the resulting neutral solution is what you get after you've titrated with acid. So you can basically understand it as just water plus salt, because that's a neutralization reaction, right? Water plus salt. So in our case, it would be HCl plus KOH. Oh, I've been doing too much math. KCl plus H2O. So water plus potassium chloride, which is a salt. So the pH of that would be significantly lower than a sample of a strong base, even though its concentration is only 0.1 molar. It's still a strong base, which means that it will yield a lot of hydroxide. Yield a lot, because it completely dissociates, right? So just like this. Compare the number of protons and the number of electrons. Since this is a atom of oxygen 18, protons equals, I don't know, I don't have the answer booklet, so I don't know what to draw necessarily, but I'm assuming it's just an atom of oxygen. An atom of oxygen gas? Or an atom of... I'll just do an atom of oxygen. I think it's just testing to see if you know valence electrons and how to draw Lewis dot diagrams. So it would just be like this. State in terms of neutrons why a water molecule containing O18 has greater mass than water molecule containing O16. Well, O18 is an isotope. Isotope of oxygen with 2 more neutrons than O16. So you can just say that there would be more neutrons in this water molecule. Shh. Oh, calm down. It's okay. Shh. She sees a squirrel outside and she goes crazy. Show numerical setup for calculating the percent composition. Okay. For oxygen. So it's 3 times. This is essentially 16. So I'm just gonna pretend like it's 16, if that's all right. And it even tells you that the GFM is 84. So this would be your setup. Determine number of moles when completely reacts, represented by reaction 1. So the molar ratio of KO2 to K2CO3 is 4 to 2. So 3.5 divided by 2 is 1.75. That's the answer. Balance, okay. Oh, I guess it's just a balance equation too. So NaHCO plus heat, Na2CO3 plus H2O plus CO2. Oh, you just need 2 of these. Yeah, okay. So for Na, you have 2. H, you have 2. Oh, what is going on? C, you have 2. O, you have 2. Na, here you have 2. C, you have 1 here, 1 from CO2. O, you have 1, 2, 3. 1, 1. You have 6. 1, 2, 3, 4, 5, 6. And then since here it's 3 times the 2, it's the same number on both sides, which means that it's balanced. Determine the volume of this sample of helium gas. The volume at 350. So it's here. It's about 5.7. 5.7 liters. On these types of questions, they're usually pretty lenient, so it's all right. Okay, so coming back to this, number 73, compare the average kinetic energy of the helium atom in 200 Kelvin to the average kinetic energy of the helium atoms at 300 Kelvin. So average kinetic energy is basically synonymous with temperature. And as we know, 300 Kelvin is warmer than 200 Kelvin. So you can just say that the average kinetic energy of the helium atoms at 300 Kelvin is higher than the average kinetic energy of helium atoms at 200 Kelvin. And here I go writing it with different wordings so that you can pick which one you want to say. Okay, so moving on, number 74 asks to explain in terms of collision theory why reacting hydrogen and nitrogen at high temperature increases the rate of reaction. So, like we mentioned just in the last question, high temperature, that means a high average kinetic energy, right? So when molecules have more energy, high average kinetic energy, they are able to essentially collide, have more effective collisions. They collide with more energy if they have more energy, right? That makes sense. Because at high temperature, they have high average Ke, which makes them be able to collide more with proper energy and orientation, which then increases the rate of reaction, right? Because reaction only happens when molecules collide with proper energy and orientation. Okay, so this one asks net quantity of heat released when 1 mole of ammonia gas is produced by the reaction. So as you can see, this reaction produces 91.8 kilojoules of energy, and this is for actually 2 moles of ammonia gas. So here's the equation they give to us. 2 moles of ammonia gas produces 91.8 kilojoules of energy. And since we want to find the quantity released when 1 mole of ammonia gas is produced, we just simply divide these numbers by 2, and you would get that the answer is 45.9 kilojoules for 1 mole of ammonia gas. Next, using the axes in your answer booklet, draw a potential energy diagram for the reaction. As you probably know, I don't want to download the answer booklet because I'm lazy. But a potential energy diagram essentially is just got PE on the y-axis, and you like something along the lines of either time, reaction, progress, or whatever on the x-axis. So as we can see here, this is an exothermic reaction with energy on the product side of the equation, which means that we have to, the diagram we draw, it has to have the product side has to be lower than the reactant side, because exothermic, that means negative delta H, right? And delta H is the potential energy of the products minus reactants. So in order to get a negative delta H, the PE has to be lower than the reactants. We have to end with less than what we started with, because this energy is released into the environment, which is why it's exothermic. So yeah, that's that. Next, in terms of activation energy and reaction pathway, why the addition of a catalyst increases the rate of reaction. So what a catalyst does is that it provides an alternative reaction pathway with a lower activation energy, right? And that is effective at increasing the rate of production of ammonia, which is like the same as increasing the rate of reaction, because it's this new pathway. Like, I'm going to draw this with the diagram I just drew here. The dotted line is going to represent the catalyzed reaction pathway. This reaction now has a lower activation energy than what it had before, which means that it's more likely for reactant particles to collide with enough energy to overcome that threshold to complete the reaction, right? So in terms of activation energy and reaction pathway, the addition of a catalyst, it increases the rate of reaction because it provides a alternative reaction pathway that has a lower activation energy, or E sub A. Alright, so next question. Identify the element present in the reactants that allows them to be classified as organic compounds. So the answer here would be carbon, right? And I hope that you learn this in class, because this is fundamentals, one of the fundamental elements in organic chemistry. So yeah, the answer here is carbon. Alright, next we have write a chemical name for reactant 1. Just circle reactant 1. We can draw this out. CH3COOH. This is an organic acid functional group. Organic acid, carboxylic acid, whatever you want to call it. And since it has 2 carbons, this is ethanoic acid. The prefix eth is for 2 carbons. Yeah. 2 carbon whatever would be eth something, and since we have an organic acid, it's ethanoic acid. Okay, next question asks for the formula of the missing product, And as we know, we have to make sure that the amount of the different molecules on both sides are the same. So we can just simply do this by counting the numbers of C's, H's, and O's we have. So we have 4 C's on the left, and we have, 1, 2, and 3 O's on the right. On the left, 2. And then H's, we have 3, 4, 7, 9, 10. We have 10 H's on the left. And then on the right side, we can count 1, 2, 3, 4 C's, 2 O's. 4 C's already cancel out, 2 O's, 3, and then we have 8 H's, 8 hydrogens. So if we compare this to the left, right, we have 10 H's on the left. That means we also have to have 10 H's on the right, 10 hydrogens. So we have H2 to compensate for the difference. And 8 plus 2 equals 10, guys. And then for the oxygens, we need 1 oxygen, right, to balance out the 3 O's. So 2 plus 1, or 1 plus 2 is 3. And 3 is 3. Yay. So, yeah, the missing product, X, is H2O. And then for the next one, identify the class of organic compounds to which this thing belongs. So, yeah, I think the easiest way to do this is to just draw it out. Alright, so drawing this compound out, we can see that this has a ester group in the middle here, so this would be an ester. Alright, next question asks about the penetrating power of the beta particle emitted from iodine-131 to the penetrating power of the alpha particle emitted from U-238. So, since we know that the alpha particles are larger, it's 4 to He compared to the beta, which is 0, -1. We know that the penetrating power of the alpha particle is less than that of the beta particle because the alpha particle is significantly larger than the beta particle, right? So when you have something that's big, it has less penetrating power. Like if you think of like a mesh screen that you have on your window. I'm not very good at drawing, so this is my best attempt at a mesh. If a bird tries to fly through, right, it's going to have a hard time flying through the mesh screen because the openings are super, super small, and the bird is pretty big, right, compared to the openings of the mesh. And then if you compare like a bird or a branch or something to like a piece of dust or pollen, right? Pollen, like the white little fluffy stuff, or tree stuff that comes out in the spring. It can, if you have your windows open, it can get through that mesh screen pretty easily, right? Because the opening is big enough for the pieces, for the pollen to come through. So, yeah, if you think about it like that, small things have greater penetrating power because they're small, so they can get through things easier than the big things. So, anyways, all in all, you just have to know that the beta particles emitted by the iodine has greater penetrating power, or you can say that the alpha particles emitted by the uranium has less penetrating power. Alright, so decay. Don't have the answer booklet again, but I'm just assuming that it's just asking for a basic reaction. So iron 59, iron is 26, not 27. Iron 59 decay mode is positron emission. So you would just 0 plus 1e, and then that makes cobalt 59, because 26 plus 1 is 27, and cobalt is element number 27, and then the mass number doesn't change because positron emission doesn't change the mass of the product. So yeah. Alright, so this asks to determine the fraction of the original sample that remains unchanged after this many days. So since iodine is the one that you use for thyroid function diagnosis, can look for is half-life on table N. We find that's 8.021. And then from here on, you have different ways that you can go about solving this. So what I would do, I think, is that I would do 24.063 divided by 8.021. So that's the total amount of time divided by the amount of time that has elapsed, right? So that should give you the number of half-lives, so that's 3. And then another method that you can use is just to keep adding 8.021 until you get 24.063. That's effective if you have like a relatively small number, but I wouldn't recommend doing that if you have like a larger number. Say if you have like 11 half-lives, that would be a lot of work. But yeah, 8.021 plus 8.021 plus 8.021. Luckily, you only need to do it 3 times if you want to do it that way for this problem. So, I mean, you could do it that way if you wanted to. And then, going back to the actual question, it asks us to determine the fraction, right? The fraction of the sample that's remained after this amount of time. So, there's also multiple ways that you can use to solve this, but I think I'm just gonna show you this most straightforward way, I think. Let me divide up the space a little first. So 84. Okay. So how you would start is that since you know that at 0 half-lives, you have 100% of everything you started with. And after 1 half-life, you have 50. Like, you just divide by 2, right? Because you're taking half away every half-life. Then 25 at 2 half-lives. And then you would have 12.5 at 3 half-lives. So, I think this is probably the easier way to do, like, when you don't have a lot of half-lives. And then for 85, it's just 241 minus 95, because americium is element number 95. So, the mass number is comprised of the protons and the neutrons. So if you have, if it tells you that the mass of this isotope is 241, you can just use 241 minus the number of protons it has to get the number of neutrons it has. Because nothing else is a part of that mass number. So that's what you can do to find your answer. So again, 241 minus 95, that is your number of neutrons, and it's 146. So yeah, that's this Regents exam. Have fun studying, and good luck on your Regents exam.